In this lecture, we want to study the solution geometry of the linear programming problem, what is the geometry behind LPP, and also how graphically we can find out the solution of one LPP. Of course, here graphical solution means we want to say if the objective function consists of two decision variables only. Of course, we can do it for three decision variables also, but visualization becomes difficult, and therefore, we will try to concentrate for the graphical solution of variables of two decision variables only. But before going to the geometry, let us just go through some definitions quickly which are required for us. One is the line segment. The line segment, the first one is the line segment. The line segment of any two points, say you have a point x 1 which we are writing as x 1 1, then x 2 1, x n 1, this is one point. There is another point, say x 2, which we are defining as x 1 2, x 2 2 and x n 2. These 2 points, obviously these 2 points are in n dimensional space, or we are calling it as R n. So, the line segment of these 2 points x 1 and x 2 in R n is the collection of points x, which we can define as x 1, x 2, x n, where x equals lambda x 1 plus 1 minus lambda into x 2. This is x equals lambda x 1 plus 1 minus lambda into x 2, 0 less than equals lambda, 0 less than equals 1. So, therefore, if you see line segment of any two points, whenever you are having x 1 which is of n dimensional points, x 1 1, x 2 1, like this way x n 1, and if I have another point x 2, that is x 1 2, x 2 2, x n 2 is a collection of such points x, x equals x 1, x 2, x n, where x can be defined as lambda x 1 plus 1 minus lambda into x 2. So, if you have a point x 1 here, if you are having a point x 2 here, the line segment joining like this, something like this, which satisfy this property x equals lambda x 1 plus 1 minus lambda into x 2, 0 less than equals lambda less than equals 1, we call it as the line segment. The next definition is hyperplane. In n dimensional space, that is in R n, if I have a set of points x, x equals say x 1, x 2, x n, this set of points x 1, x 2, x n, if they satisfy C 1 x 1 plus C 2 x 2 plus C n x n equals z, then this C 1 x 1, C 2 x 2 plus C n x n equals z, this defines one hyperplane for a given values of C i and z. So, basically if some values of C i and z are given, if I have a set of points x equals x 1, x 2, x n, then C 1 x 1 plus C 2 x 2 plus C n x n equals z will represent one hyperplane. In particular, if you take if z equals 0, that means in matrix notation, if I am writing C x equals 0 and this C x equals 0, we can tell that this passes through the origin, or in other sense this C x equals 0 means C passes through, this hyperplane passes through the origin, and in that case we can tell C is orthogonal to x. C is orthogonal to every vector x in the hyperplane. In general, we C is called the normal to the hyperplane. The next one is parallel hyperplane. What happens actually, if I have two hyperplanes C1 x equals z and C2 x equals say not z, say this is z1 and this is z2, then these two hyperplanes will be parallel if C1 is written as C1 equals lambda C2, of course, where lambda is not equals 0, or we can say that if they have the same unit normal. Two hyperplanes are parallel if we say that they have the unit normal, then these two are the parallel hyperplane. The next one is closed and open space. The closed and open space is defined like this, where I am just denoting it H0 plus. This is equals x such that I am just telling C x greater than z and x such that C x less than z. This we call as the open half space, and whenever you are having this one x such that C x greater than equals z second bracket and x such that C x less than equals z, then this we call as the closed half space. So, basically this relates, if you understand in terms of LPP, if you have to say, then we have the constraints of the form A x greater than equals b. So, the closed half space and open half space basically related to your the constraints. So, H 0 plus, whenever we are strictly talking about the inequality, whether it is greater than or it is less than, we call it as the open half space, whereas whenever we are considering equality as well as inequality together, that is x such that C x greater than equals z and x such that C x less than equals z, then we call it as the closed half space. For example, if you take C, if C equals 4 and 5 and say z equals C equals 4 and 5 and z equals 8, then H plus I can write it as 4 x 1 plus 5 x 2 greater than equals 8. This one you may tell as positive closed half space, since we have considered here as greater than equals. So, this we call as positive closed half space, whereas if you take, I am just writing it as H minus, then this will be 4 x 1 plus 5 x 2 less than equals 8. This we may say as negative closed half space, negative closed half space. So, basically to represent the constraints, we are representing it by the half space. It may be open half space, it may be closed half space, it may be on the side of the right side below the line, or it may be above the line. This we will come whenever we are trying to find out the graphical solution of the system. We will talk about these terms. Now, let us come to the next definition, that is convex polyhedron. Convex polyhedron. Usually by definition, if I have to tell, I can tell that the set of all convex combinations, the set of all convex combinations of a finite number of linearly independent vectors, the set of all convex combinations of a finite of a finite number of, this will be of a finite number of linearly independent vectors is called the convex polyhedron. So, basically whenever you are having the number of linearly independent vectors, if you take any convex combination of these vectors, then you will obtain one convex polyhedron. Mathematically, if I have to say, if I have a set of points x in R n, that is n dimensional space R n, x equals x 1, x 2, x n, these are linearly independent set, then the set which can be represented as not x here, you have a set of linearly independent vectors x 1, x 2, x n, then the set x such that x equals summation I equals 1 to m lambda I x I, where lambda I greater than equals 0 and summation over I equals 1 to m lambda I, this is equals 1. This we call as the convex polyhedron. So, basically again it relates with the feasible region of the linear programming problem. Feasible region we can obtain from the linearly from the constant set, and from there we can obtain the convex polyhedron. So, whenever you are having m linearly independent vectors, then x 1, x 2, x n, then x equals summation over I equals 1 to n lambda I x I, and lambda I greater than equals 0, I equals 1 to m, lambda I equals 1. This we call as the convex polyhedron. The next one is convex hull. You consider a subset Y which is a subset of n dimensional space, that is R n. Then the smallest convex set containing this Y is known as convex hull. So, I think it is clear that the smallest convex set which contains the set Y, we call it as the convex polyhedron. So, convex hull. The convex set which contains Y is called the convex hull of a set. Now, let us come to the next point, that is geometry of LPP. The what the one LPP represents geometrically, let us take one problem, maximize Z equals C transpose X subject to A x equals B, where x is greater than equals 0. Your C matrix I can tell C 1, C 2, C n, x is equals to the elements x 1, x 2, x n. A is a matrix A I j, I can represent it as m cross n matrix, and your B is equals to B 1, B 2, B m. So, we are having one LPP maximize Z equals C transpose X subject to A x equals B, where C represents the matrix C 1, C 2, C n, X represents the matrix X equals x 1, x 2, x n, A is the matrix A I j of order m cross n, and B equals B 1, B 2, B m, this is the B matrix. Now, geometrically basically what we want to say, let us take the constraint of the form A x equals B, this is the first one I can say. The constant A x equals B, basically this can be divided into two parts, two inequalities, A x greater than equals B and A x less than equals B. So, the number one conclusion we can made is each constraint defines a half space. I think it is clear why we are telling from the definition of the open half or the closed half space, whatever we have just defined. From there we can tell it takes the form of the half space, because I am talking very particularly half space because it may be open half space, it may be the closed half space depending upon whether A x is greater than b or A x equals greater than equals b depending upon that one. So, each constant basically represent one half space. Number 2 now come, I am just first writing, then because it will be easier for you. The feasible region of the LPP is the convex polyhedron defined by intersection of half space. So, if you see what is the feasible region, the question will come, what is feasible region? You are having the half spaces, half space represents the constraints. So, whenever you are taking the equality of each half space and you are drawing the lines, so there will be the intersection of the lines, and the intersection which is common among all the constraints, that region we basically call as the feasible region. And therefore, the feasible region will form one convex polyhedron. Please note this one, that this will form one convex polyhedron. Convex polyhedron means if you take any two linearly independent vectors, if you join it, then that will also be a convex inside that one. So, the basic advantages of this I will come next, that how it helps us using some theorems. Number 3. So, basically each constraint is defining one half space, feasible region we are obtaining, which is a convex polyhedron, that is which takes a particular form, and the next one is the your objective function. Your objective function is this one. Objective function is a, again it is clear, if you see the form of the objective function z equals C transpose x, then this represents one hyperplane. So, now you see the problem, maximize z equals C transpose x subject to A x equals b. Your objective function is representing one hyperplane. Whenever if you take a particular value, I can tell that C transpose x, this is equals k for a given value of k. The graph of this equation basically will represent one hyperplane, where k represents the distance of the origin from the hyperplane. So, in other sense, if you have a curve like this, say this is the hyperplane C transpose x equals k for a particular value of k. So, what is k? K is the distance from the origin of the hyperplane. Why the distance is required? Whenever we are trying to find out the graphical solution, then that will be clear to us. So, the objective function is represented by a one hyperplane of the form C transpose x equals k, where k is the distance of the origin from the hyperplane, and we will try to move away the value of k from origin as large as possible for maximization problems, or the opposite one for the minimization problem. So, this is the geometry of the objective function. For the constraints, already I have told that the each constraint represents one half space. It may be open half space, it may be closed half space, and once you have the half space, the intersection of all these half spaces or the constraints will give one region, which we are calling as the feasible region, and by definition the feasible region will be a one form one convex polyhedron. So, basically this is the geometry of this one. There is another one, that is extreme point. This extreme point, sometimes we call it as corner point, or we call it as vertex also. Sometimes we call it as corner point or vertex. Now, a point of intersection of two bounded lines means two bounded lines of half spaces, we call it as the extreme we call it as the extreme point or the corner point or the vertex. If it is not clear, then you can see I am just writing a point of intersection of two boundary lines. I am telling two boundary lines, or I can say or half spaces, that is between two constraints in other sense, of course, which is also a part of feasible region, is known as the extreme point. Let us take one example. I think from the example it will be very clear to you. Suppose I want to maximize 3x plus y subject to the constraints x plus y less than equals 4, x plus 2y less than equals 6, and from the physical viewpoint x y greater than equals 0. So, to find out the extreme points, at first I have to draw the lines in the equality sign, or in other sense you draw the lines for x plus y equals 4 and you draw the line for x plus 2 y equals 6. So, if I draw a graph, just this is the origin, it will go up to 6, 1, 2, 3, 4, 5 and 6. On this side I am making 1, 2, 3 and 4. So, there will be a line which will be passing through 4 and 4, which will be passing through 4 and 4. This is basically the line x plus y equals 4, that is 4 0 and 0 4 is the point. For the other line it will pass through, I think x y is 0. So, 6 0 and 0 3. So, it will be something like this 6 0 and 0 3. So, I am just drawing the line, this one. So, this line is x plus 2 y equals 6. Now, you see what will be the feasible region from here. Let us explain this one. You have a line x plus y less than equals 4. That means, the direction of this line x plus y equals 4 will be this one. That is, it will come below this side. That is, since it is less than equal, so from the line on the left side it will go, otherwise it will go on the right side. The next one is x plus 2 y less than equals 6. So, we have drawn the line for x plus 2 y equals 6, again below the line. On the left side of the line will be the satisfying this one, and we have another two conditions, x greater than equals 0, y greater than equals 0, or we can tell the first quadrant only, the positive quadrant only. Therefore, the feasible region I can mark it something like this. This will be your feasible region. So, once I am getting the feasible region, the extreme points are the, as I have told, intersection of two boundary lines. So, O is a feasible, O is extreme point, here A will be another extreme point, B is another extreme point and C is another extreme point. By solving the equations, I can obtain two different equations, I can obtain the values of O, A, B and C. Just like your O is of course the origin, your A is very clear, that is point A will be 4 0. Point B, if I solve these two lines, x plus y equals 4, x plus 2 y equals 6, I will obtain, I think if I am not wrong, B equals 2 2 and C is 0 3. So, these are the extreme points, and so from this example I feel it is clear how to draw the, or how to find out the feasible region. Once I have obtained the feasible region, the corner points, these I am calling as extreme points, where basically it is meeting the boundaries. Say for point A, this x axis and the line x plus y equals 4, wherever they are meeting, that point is A, and similarly to other points B and C. So, from this I can find out what is my extreme point. The next one is the basic solution. If I remember correctly, I think I have talked about this basic solution in the last lecture. In short, I am telling you. So, you have a system of equations A x equals b, where A is A I j m cross n. I am assuming A is m is less than n, and rank of A is m. So, now we can form a matrix B, which is also of the order m cross m. This matrix B is formed by taking the m linearly independent vectors or columns of A. Since the rank of A is m, therefore, A is having m linearly independent columns. So, you take m linearly independent columns from A, and I am making matrix, I am preparing a matrix B of order m cross m. Now, in this matrix B, if I am making n minus m variables, this is equals 0, n minus m variables, this is equals 0, which are not related to the columns of the rank of A or whatever we have taken in B. And then if we find a solution, then the resultant solution is known as the basic solution. So, since the rank of A is m, so we are taking the m equations and all others variables we are taking as 0, n minus m variables, then we are finding out the solution, and that solution is known as the basic solutions. Once we obtain the basic solution, then I can go for the basic feasible solution. Basic feasible solution. So, already I know what is the basic solution of what is the feasible solution of one LPP. So, if a feasible solution of an LPP is also a basic solution, then that solution is known as the basic feasible solution. So, I am finding out the basic solution, I have the feasible solution, which already we have done, and if the feasible solution is also a basic solution, that one is known as the basic feasible solution. Now, let us go through some theorems. I will not give the proofs of the theorems, I will make the statements and the consequences will be used afterwards. The set of all feasible solutions, of a LPP is a convex set. Set of all feasible solutions of a LPP is a convex set. Already we have told what are the definition of the convex set. Whenever you are having the convex sets, so if you take any linear combination, that will also be a convex set, and therefore, the set of all feasible solutions will form one convex set. This is the first theorem, that if you take any feasible solution of the LPP, that will give you the convex set. The next theorem is the objective function. The objective function of a LPP, assume, just see this one, assume its optimal value, at the extreme points, of the convex set, of feasible solutions. Just see the beauty, that we are telling that our basic aim is to find out the solution of one LPP. the LPP is consisting of the objective function subject to the satisfaction of some constraints, and we want to find out the value of the optimum value of the objective function. By this theorem now we are saying that the objective function takes its optimum value only at the extreme point of the region, feasible region. So, you see in the feasible region I do not have to check all the points, I have to check only the extreme points whatever we have discussed. I know now what is the extreme point or the corner point. So, at the extreme points you check the value of the objective function and you find out whether that optimizes, which point optimizes the objective function. Of course, I may say that you may get the optimum value at more than one extreme point also, that part we will discuss later. So, from this theorem I do not have to check any other thing except the extreme point for obtaining the optimum value of the objective function. The next theorem says a basic feasible solution, to LPP corresponds to an extreme point, extreme point, this is TRE, extreme point of the convex set of feasible solutions, of the convex sets of feasible solution, and the converse is also true. This is another thing. So, a basic feasible solution is the optimal solution, and here we are telling a basic feasible solution is corresponding to nothing but the extreme point. So, once I know the extreme point or from there I can find out what is the basic feasible solution, and from the basic feasible solution I can tell what is the optimum value, and the converse is also true, that is if I know the other way around then also I can tell the same part. The number 4 is the objective function assumes its optimal value at more than one extreme point, at more than one extreme point. The objective function assumes its optimal value at more than one extreme point, then every convex combination, of these extreme points gives the optimal value of the objective function. So, if you see from here, now we are telling by this theorem the objective function assumes its optimal value at more than one point, then you take any convex combination of these 2 points, then you are getting a set of points. At each point also you will obtain the optimal value. That is, in other sense you can tell that there will be infinite number of optimal solutions of the given LPP. So, if these 2 of the extreme points where it is optimum, so if I make any convex combination of these 2 points, any point you take at any point, the value of the objective function will become optimum. So, these are some theorems through which I can go for the graphical solution, and of course, there are some other theorems also. This fundamental theorem of LPP. Before going to the simplex method in the next lecture, I will just go through this one. Let's come to the graphical solution. Come to the graphical solution of LPP. As I told at the very beginning, I want to find out I can find out the graphical solution of the LPP whenever the objective function is consisting of two variables only, because you can draw the graphs in 2 dimension. Of course, for 3 dimension, that is if I am having 3 decision variables, then also we can plot the graph in 3 dimension, but it will be little bit complicated. Beyond 3 dimension, it is not possible to find out the graphical solution of LPP. So, in general, to find the graphical solution, we take those problems where the objective function consisting of only 2 variables. Here we use 2 methods, one is the search method and another one we call as ISO for fit or ISO cost function. So, I will explain these 2 methods separately. The first one, let us go to the that approach we are calling as search approach. For your convenience, I am just telling number 1, you convert, in short I am writing, I am not writing in details, convert the inequality constraints, into equality constraints. Inequality constraints, you transfer it into equality constraints. Once you have converted the inequality constraint into equality constraint, you can draw the graphs or draw the lines very easily. A x equals b, I can draw the line easily. So, this is the first approach, that convert the inequality constraint into equality constraint and draw the lines for each equality. So, this is the first step. Your next step is, and of course, once you are converting, draw the lines, then intersection of these lines will give you the feasible region also, which I have already told by one example. So, in the first part, you are converting the inequality constraints into equality constraint and then you are drawing the lines, and the intersection of these lines will give you the feasible region. Once you have the feasible region, that feasible region, basically I can say that this feasible region may be bounded or it may be unbounded. You have to note this thing. Through example, we will explain. The feasible region may be bounded and the unbounded. So, after seeing this, now you calculate the extreme points. I think that you can find out what are the extreme points from the feasible region. Now, this is the second step. Now, in the third step, find the value of the objective function at each extreme point. Find the value of objective function, at each extreme point, So, once I have obtained, then you select the extreme point, I am not writing this one, you select the extreme point which corresponds to the optimum value of the objective function and you got the solution of the function. So, select the objective function which optimizes best the objective function. So, let us recapitulate again. In the search approach, basically this is the easiest approach. Your first step is you have to find out the feasible region. How you will find out the feasible region? You take the inequality, convert the inequality into equality and draw the lines. Intersection of the lines will give you the feasible region. Once you obtain the feasible region, obviously you can calculate what are the extreme points of the feasible region. Once I have calculated the extreme points of the feasible region, at each extreme point I will calculate what is the optimum value of the objective function. What is the not optimum? What is the value of the objective function? And once I obtain the value of the objective function at each extreme point, the extreme point or points which is giving you the objective function, optimum value of the objective function, that one we call it as the optimum solution of the given LPP. But this way we can find out the graphical solution consisting of two decision variables of the objective function only. The next one is the ISO profit, or we call it as ISO cost approach. Obviously, for maximization problems we use ISO profit, for minimization problems we use the ISO cost. Now, step 1 and step 2 are same as I have told for the search approach. That is, in both step 1 and step 2 you are finding out, you are converting the inequality constant into equality constant, you are drawing the lines, the intersection is giving you the feasible region, from the feasible region you are calculating the extreme points. Up to this it is same. Point number 3, what happens? We have to choose a convenient profit function which takes the form of the, again I have discussed this one, objective function takes the form C transpose x equals k for a given value of k and which lies inside the feasible region, that is at least at one point it touches the feasible region. Now, this is the third step. So, you are drawing a line for the objective function which takes the form C transpose x equals k for a given value of k and which is passing through your feasible region. Then move this line away from origin parallel to the original line as far as possible, and you see where it is touching the objective function at least one and it is giving you the maximum value. Or in other sense, if I can draw a curve like this, something like this is there. So, this is your say objective function. You may draw a profit function, I am talking about ISO profit. So, the value of k should be as large as possible, or in other sense from the definition of the hyperplanes also you can say that the value of k should be as large as possible, or the distance of this profit curve from origin should be as large as possible. So, you are moving it further, you are moving it further, it may happen you are moving like this way where it is touching at this point, this one, and here you may get the optimum value. So, the basic difference is you are generating one profit line for the objective function of the form C transpose x equals k, and for the profit maximization problem you are moving it away from origin parallel to the original ISO profit curve, moving it further till it reaches at least one or more than one point. After that, if you draw the line, it will go outside the feasible region. Just like after this, if I draw, it may go something like this, which does not fall in the feasible region, because your feasible region is up to this. So, this is the basic difference. Of course, in first approach directly by calculations you can obtain the solution of the system. So, this is the another approach. Now, let us take some examples, because without example this you will not be able to understand very easily. Let us take the example of maximize z equals x 1 plus 3 x 2 subject to 3 x 1 plus 6 x 2 less than equals 8, 5 x 1 plus 2 x 2 less than equals 10, x 1 and x 2 greater than equals 0. You may ask, why always we are taking x 1 x 2 greater than equals 0. In LPP we want to find out the solution of the real life problems. In real life problems usually the decision variables cannot take the negative values, or usually they take the non negative values. If you consider time, time is always positive. So, we take this example that this consideration constant x 1 and x 2 should be greater than equals 0. We want to find out the graphical solution of this particular problem. Let us take the first approach, that is the search approach. You can consider these two lines as 3 x 1 plus 6 x 2 equals 8. You can write it in the intercept form also to draw the lines, that may become easier for you. So, these two lines, that is x 1 by 8 by 3 plus x 2 by 4 by 3 is equals to 1. Similarly, for the second one, x 1 by 2 plus x 2 by 5 equals 1. So, you can draw the lines, I am not talking about that part. Let us draw the graph. So, this is your origin, say 1, 2, 3, 4 and 5. On this side also 1, 2, 3, 4 and this is your 5. So, one point I think we will go through 2 and 3. So, if you draw the line, it will be 2, 3. Another point will be going by 2 and 5. This is your 5. So, this is the 5, this is the 2. So, if I draw the curve something like this, it will come. So, these two lines are there. For both the lines, it is less than equal sign. So, approach is this one. So, direction will be on this. If it is greater than equals, then direction will be on the other side. So, this is less than equals, this means that this half. For this line, this is on this half, and x greater than equals 0, y greater than equals 0. So, therefore, this is the feasible region. What are the extreme points of this feasible region? One is O, another one you can tell this is A, this point is B and this point is C. The value of this you can calculate easily. O is 0 0, your A will be 2 0, B is 11 by 6 and 5 by 12 and C is 0 4 by 3. So, these are the extreme points O, A, B and C. Once I have obtained A, B, C, now as we have told, our last step is find out the value of the objective function at O, at A, at B and at C. I am just writing Z O, this will be 0, Z A, this is equals 2, Z B, this is equals 37 by 12 and Z C, this is equals 4. So, you can say that Z max value of these extreme points will be Z C and which is equals 4, and the vertex C is 0, 4 and 3. This maximizes this objective function. I think it is clear from the example how we are obtaining the solution of this approach. Now, so this is your search approach. Whenever you are this point C, you are telling, whenever I want to do it in the isoprophet approach, you will find out a solution equation of x 1 plus 3 x 2 equals k. In particular case, say x 1 plus 3 x 2 equals 1. Say this line is the dotted line, this one, this is your, this is the function for z, and this you are moving further like this way. Maybe at some point it will go, it will cut like this only by touching the point C, and after that it will move it further away. So, your C will be the optimum value of this one. So, by this way I can obtain the solution of this graphical solution of this one. I think it is clear that you find out the feasible regions of the by drawing the lines of an intersection. From the feasible region, draw the extreme points. At the extreme points, calculate the value of the objective function, and wherever it gives the maximum value or minimum value, that is the optimum point where you are getting the optimum value of the given LPP. Now, let us take another example. Maximize z equals x 1 plus x 2 subject to x 1 plus x 2 less than equals 1 minus 3 x 1 plus x 2 greater than equals 3 and x 1 comma x 2 greater than equals 0. Let us take this one. There will be a curve like this. I am not now plotting everything 1 0, this will be 0 1. This is the line x 1 plus x 2 equals 1. Here there will be a point minus 1, somewhere here there will be a point 3. So, this is the thing. So, there will be another line like this. This line is minus 3 x 1 plus x 2, this is equals 3. Now, what will be the feasible region? In this case, x 1 plus x 2 less than equals 1, that is arrow will be on this side, that is this side, this lower half, the left hand side of the line, whereas minus 3 1 plus x 2 is greater than equals 3. That means, the arrow will be on this direction, that is on the upper side of the line. So, if you take for the line x 1 plus x 2, basically if I take intersection between x 1 x axis and x 2 axis, this is your x 1 axis, this is your x 2 axis, then this is the intersection of the line x 1 plus x 2 equals 1 and x 1 and x 2 axis, whereas for this line this will be the intersection. If I make this 2, so it is becoming null set. So, I can tell that feasible set is empty. So, once feasible set is empty, then obviously the LPP has no solution. So, please note that this LPP has no solution. So, why no solution? Because the feasible set is empty, there is no feasible region. The feasible region here is empty, because thus now we have explained this thing. So, I can say that infeasibility will never occur if all the inequalities are of less than equals type, then infeasibility will never occur. So, there will be feasible solution always if the less than equals, all the constants are less than equals type, but if it is less than equals, if it is greater than equals, something like this, there may have solution, there may not have solution. So, it is not that every LPP problem has a solution, just like I have told in the first example, there is only one optimum point where you are getting the value of the objective function as optimum. In this second example, what happens? There is no solution of the problem, because the feasible region is empty. And you take this one now, maximize z equals 6 x 1 plus 10 x 2 subject to 3 x 1 plus 5 x 2 less than equals 10, 5 x 1 plus 3 x 2 less than equals 15 and x 1 x 2 greater than equals 0. Let me plot it. There will be a point 3, there will be a point 2 here, there will be a point 5 over here, here it is 4. So, there will be a line between 5 and this is 3. So, there will be a line like this 5 and 3, that will be a line between 2 and which will pass through any point, some point in between 2 to 3 by 4, and both are less than equal. So, this is also this side, this is also this side. So, your feasible region is this one. So, here you are having O, A, B and C. If you see O, A, B and C, if I calculate, that is 0 0, your A point is A is 3 0, your B is, if I calculate, it is 45 by 16 and 5 by 16, and your C is 0, 2. If you calculate these values, z is 0, z a is 18, your z b is 20 and z c is also gives you 20. So, you see now, for this case I am getting 2 points B and C in the two extreme points where the value of the objective function is same. So, at the point B also it gives you optimum value, at the point C also it gives you optimum value. If you recall one theorem that on the if I have the optimum solution at more than one point, then any convex combination of these 2 points also will give you the optimum point. Therefore, if you join the line B and C, that is here in this example this line dotted this line B C, you take any point in B C, always you will obtain the optimum result. Or in other sense, we can say that this LPP is having the multiple solution, or I can say infinite number of solutions. I can say infinite number of solutions. So, now we are coming 3 different types of solutions. If you see 3 different types, there will be only one optimum point where you will get the solution of the optimum value of the objective function. There may have situations where you will obtain more than one optimum point where you are getting the same optimum value of the objective function, that is you are obtaining the maximum or infinite number of or multiple number of solutions. And the third one is the 0 no solution, whenever the solution space is empty or there is no feasible region is empty. So, 3 type of solutions can occur, only one optimum point, more than optimum point, or no solutions, multiple optimum points, single optimum point, or no solutions. In the next class we will start with the unbounded solutions and then we will go to the simplex methods also. Thank you very much.